Hello, pre-calculus students. Today we're going to talk about section 9.3, which is polar and rectangular coordinates. So we're going to be talking about switching between those two different forms today. You'll need pencils, highlighters, your notes, a unit circle, and a calculator. Okay, make sure that you're trying the examples as we go. It will make your life a lot easier. Okay, let's get started. So, converting between polar and rectangular coordinates. So polar coordinates are the form r, comma, theta, and we want to talk about how to write them in the form x, y. Okay, and I have some conversions going on up here. And so if we were to take a look at one of these examples, and how could we find out what the x is, and how could we find out what the y is? Let's just come up with maybe a more simple example. So let's say I gave you the coordinate 2 and then pi over 3. And we were to sketch that, okay? So here's 2, right? And then pi over 3 would be like here. So here's my 2 pi over 3. Okay, what I'm looking for here is how could I find out, this is it, how could I find out the x and the y values to get there? So instead of the rotation and the radius, how could I find out my x and my y values? So you see how we have this right triangle. And we know that this is 2, and we know this angle is pi over 3. And this is right triangle. If I want to get this x value here, then in relation to this angle I have, this is adjacent and this is hypotenuse. So to get this x, I could write adjacent hypotenuse. I could say something like cosine of pi over 3 equals adjacent over hypotenuse. And to solve, I can multiply both sides by 2. So x would be whatever 2 times the cosine of pi over 3 is. So 2 was my radius, pi over 3 was my angle. To find my x value in general, what I can do is the radius times the cosine of the angle. That should sound super familiar from chapter 8, right? That's how we found the horizontal component. Now, if I wanted to figure out this angle here, how much I have to go up or down, and I know my hypotenuse and I know my radius, then I could write a sine ratio, right? I could say the sine of pi over 3 equals y over 2 and multiply both sides by 2. And so y is 2 times the sine of pi over 3. Okay, 2 is my radius, pi over 3 is my angle. My y value is always r equals r times the sine of pi over 3. That makes sense. That was your vertical component from before. Okay, so that's how I can go from rectangular or from polar to rectangular. And that's what example 1 is asking me to do. It's asking me to find the rectangular coordinates, the x and the y, given these polar coordinates. Okay, so I know to get my x value, it's r times the cosine of theta. So it's going to be negative 2 times the cosine of negative 5 pi over 6. And to get my y value, it's going to be negative 2 times the sine of negative 5 pi over 6. Okay, just how you found the components last chapter, but instead of being in those little pointy parentheses, now it's just a rectangular coordinate. Now, it doesn't say this here. A lot of times in the directions on a quiz or a test, it would say find the exact rectangular coordinates. That means no decimals. It means use the exact values from the unit circle. Okay, so this becomes negative 2 times, okay, the cosine of negative 5 pi over 6. So, okay, if 5 pi over 6 is this rotation, right, from here to here, then negative 5 pi over 6 is this rotation, and I wanted the cosine, so negative root 3 over 2. Okay, so 2 times negative root 3 over 2. And then this would be negative 2 times the y value there was 1/2. It was negative 1/2, right? Yes, it was negative. Okay, and then we would simplify that. Okay, so here the 2's cancel, and negative times the negative is positive. So that would be root 3 comma 1. So that would be the corresponding rectangular coordinate for that polar coordinate. All right, so go ahead and try the next one. But it's the same idea, right? We're going to do 3 cosine 270 and then 3 sine of 270. At 270, the cosine is 0. At 270, the sine is -1. So that would be 0, -3. And that might be something too, you're thinking, okay, that one's on an axis. If it was a polar coordinate, you might be able to say, okay, I can kind of visualize it, 270, it's here. You might just think in your head, oh wait, that's just 0, -3. And if you come up with that, then that's totally fine. Okay, so now find the polar coordinate of each of these points. So these are just rectangular coordinates. So this, for example, is just the point 2, -4 right here. Well, what I want to know is, what is this rotation, right? And I want to know, what is this length? So I want to think of it as one of our little triangles. And this is my -2, and this is my 4. Well, to get my radius, I would have to use the Pythagorean theorem, right? I have to do r squared equals -2 squared plus 4 squared, and then take the square root. And that's how we're going to find our radius in general, and it's up here. R is the square root of x squared plus y squared, just like magnitude, last chapter. Okay, so let's get our R. It's the square root of a squared plus b squared. Notice I'm just putting that -4 in parentheses before I square it. So this is 16, that's 4, so r equals the square root of 20, which you could write as 2√5, or it's about 4.5. Decimals are fine. If it doesn't say exact, it's fine. And then I need to know this angle. And so if I want to know just this angle here, I could do, this is opposite, this is adjacent. I could do tangent and then take the inverse tangent, but then I have to think about the quadrant. So the way I would get this angle is to do the inverse tangent of 4 over -2. Well, that's the inverse tangent of my y value over my x value. This is like when you found the angles, the direction angles, when you were doing vectors. Okay, so you'll see here, theta is the inverse tangent of y over x. Now here it says sometimes you have to add pi, and depends on what your x value is. You can memorize those rules, or you can really just think about, I need my final answer to be in the correct quadrant. All right, so my angle is the inverse tangent of y over x. So when I put that into my calculator, I get -63.4 degrees. You guys, I drew this wrong. My radius is right. Dang it. How many of you are like, for so long, when is she going to figure this out? Okay, my radius is still the same. I was looking at my angle and I was thinking to myself, the reason I knew I was wrong is because that angle's in the 4th quadrant, but I had drawn it in the 3rd quadrant, so I knew something was wrong. Okay, so would this work if I were to write this as a coordinate 4.5, -63.4? Because now remember, this is asking for a polar coordinate, so your answer needs to be written as a coordinate. So it's not like with vectors where you could say my magnitude is this, my direction angle is this, and then you didn't have to like connect them with any sort of notation. This you do. So when you go to write your final answer, does this make sense? To have a radius of 4.5 and an angle of -63.4 degrees. Would that get you to this point in the 4th quadrant? Sure, I could go back to -63.4 and then a radius here. Now, could you follow the same rules as you did with vectors where you'd have to, if it's in the 4th quadrant, add 360? Absolutely, it would be equivalent. Okay, so there's more than one way to name all of these points, but you do need to double check that your angle of your, or the quadrant of your original point and the quadrant of your converted point are in the same quadrant, Whew. All right, so part B. This one is in quadrant 3. And so you might even want to make a note of that. This is quadrant 4. Okay, is this in quadrant 4? It is. This guy is in quadrant 3. So I want to make sure when I get my final answer, it's in quadrant 3. Okay, so to get my radius, I'm going to do the square root of -8 squared. Oh, wait, no, I didn't. Sorry. The -12 squared. I was thinking over here I had written this down wrong, but I just drew it wrong and then labeled it wrong. Okay, so this ends up being, just put that in my calculator, 14.4. That's my radius. All right, my angle is the inverse tangent of y over x. So remember, inverse tangents from chapter 6 are always, if you're in degrees, going to fall between negative 90 and 90. So this is going to give me an angle of 56.3 degrees. Now, if I were to plot something in the third quadrant, does it make sense that the angle is 56.3 degrees up here and then a radius of 14.4? That would put it in the first quadrant. Okay, this is in quadrant 1, but my point is supposed to be in quadrant 3. So I have to add 180 degrees, just like we had to do with vectors last chapter. Okay, so in this one, we didn't end up having to because that negative rotation is still in quadrant 4. So then I could write this as 14.4 comma 236.3 degrees. You always check your quadrants. All right, now the next two examples have us going from polar equations to rectangular equations. So when it asks us to do that, what it means is it's going to give us equations that are in polar form. That means they're written in terms of r's and thetas. And it wants us to give our answer in rectangular form, which means our answer is written in terms of x's and y's. And so to do that, we're going to use the conversions that are at the top. I'm going to rewrite them here, but I'm going to use the fact that I know x equals r times the cosine of theta, and y equals r times the sine of theta. I also know r is equal to the square root of x squared plus y squared, which gives me a bonus. This is kind of like when we did identities of r squared equals x squared plus y squared. Okay, so it's in some ways like identities where we're swapping things in and out to get an equivalent expression or equation in this case. All right, so when I look at this one, it's in polar form. I want it in rectangular form. That means all r's and thetas need to be gone in favor of x's and or y's. And I see a cosine, and I think, all right, if I could have an r times the cosine, then I could swap it out for an x. But I don't see an r. So I'm going to use an algebra trick. What I'm going to do is I'm going to multiply both sides by r. And that's going to give me r squared equals 6r cosine theta. All right, well, I know r times the cosine of theta is x. So over here I'm going to have 6x. And I know that r squared is equal to x squared plus y squared. So over here, this is going to be x squared plus y squared. Now, I'm going to leave it like this, which is going to seem really strange, but you might remember from last year when you did conic sections, sometimes you would have equations that would have x squared and y squareds and x's, and we would kind of leave them and then we'd write them another way. We're going to get into that in the next chapter. Okay, so for now, I've eliminated r's and thetas in favor of x's and y's. We're going to leave it. Okay. Now the next one, r equals -3. Okay, well, I see an r, that's the only variable I see, and I know r equals the square root of x squared plus y squared. And so I'm going to put this, right, here's my r, I'm going to put that square root of x squared plus y squared in there instead. Now, typically with this, we do want to get rid of the square root, so if I square both sides, I get x squared plus y squared equals 9. You might recognize that this is a circle with a radius of 3, and here you should recognize that's a radius with a circle of 3. You saw that a little bit last year with circles when you did conic sections. Okay. Now, these can be different. So this is just a couple, and you might get into some of the homework and be like, hang on, this looks different than what we did. Sometimes they just are. You might have something like, let me make up another one. You might have something like this, r equals 5, and then it might be times the cosecant of theta. And you might look at that and say, well, what am I supposed to do with that? There aren't any cosecants up here. Okay, well, remember back in chapter 7 when we were doing identities, rewrite it in terms of sines and cosines. I'm looking for something like an r cosine or an r sine, and then I can swap it in x's and y's instead. So here this would be 5 times 1 over sine of theta equals r. And then look what happens when you multiply both sides by the sine of theta. Here you get a r sine of theta equals 5. And you know r sine of theta is y. So this could just be rewritten as y equals 5. Okay, so they will vary. The more you do them, the easier they end up getting. All right, couple more going the other direction now. So now, if I give you something in rectangular form, so it's in terms of x's and y's, I want my answer to have r's and or thetas. Might not have both, okay, but one or the other or both. All right, so I'm going to use those same conversions I did before. I'm going to jot them here at the top. Whoops, x equals, just so that I don't have to keep flipping. And then we had r equals the square root of x squared plus y squared. And we had r squared equals x squared plus y squared. Okay, so I don't really see any of these x squared with these expressions in here. What I'm going to do is I'm going to expand this. So this x minus 3 squared, take a minute and do that. Think of it as x minus 3 times x minus 3, make a box. And you should get x squared minus 6x plus 9 plus y squared equals 9. All right, so then I have x squared plus y squared minus 6x equals, those cancel, equals 0. Okay, I know x squared plus y squared is r squared. And I know 6x, so I know x is r cosine theta, so I can put that in there. And then usually if we can, we try to solve for r. Here, I notice I could pull an r out as a factor. Some of you might be thinking, I want to cancel an r out of everything. I get it. I'll talk about it in a second. Once I have r equal to 0, and then I have r minus 6, whoops, this would just be cosine theta. I could solve this equation and get r equals 6 times the cosine of theta, and then this is just r equals 0, which is just a point at the origin. This is not just a point at the origin, right? So we end up throwing this out because it's not possible. So probably you guys were saying, well, I was going to cancel it out anyway, and I was just going to get this, so that would be fine. In this case, it ends up not mattering if you do that, because this will always just be a point at the origin, which is not what that would have been anyway. But in general, if you do that when you're solving an equation, just cancel it out, you would have lost a solution, right? You would have lost the solution 0, like if it was just a regular equation. So that's just not a good habit because of that. But in this case, if you had, it wouldn't have been the end of the world. All right, one more example, same idea. I would expand this. So I have x squared plus y squared minus 2y plus 1 and then equals 1. The ones cancel. Again, this x squared plus y squared is r squared minus 2 times, now this would be r sine of theta equals 0. And then really it's the same thing as what we just did. I would pull the r out, set my factors equal to 0, and then I would get my solution. Again, we would get rid of that one. Okay, so these are things that you need to know, right? And it should be in the back of, you should still have it fresh, right? Because we used all those same things back in chapter 8. And it takes care of section 3.